Physics 2048 Final Exam Review Study Union. My name is Giovanni. This is Del Barco's Physics Review. I want you to know that you can go to this website to find the review that we're going to be doing. I'm going to be skipping around in the questions to get all of the topics done, and then if we have more time afterwards, I'll go back to the ones we skipped. All right. So we're mainly going to be focusing on rotational kinematics, torque, angular momentum, and oscillations. Okay, so I'm actually going to skip this problem. I'm going to get to this one. All right, so this is going to be rotational kinematics to start with. Bob is driving his super awesome car. He starts in reverse and ends driving forward. The angular velocity of the tires when he is reversing is 20 radians per second, and the angular velocity when he is driving forward is 30 radians per second. He performs this with a constant angular acceleration. It takes Bob 5 seconds to make this change in velocity. The radius of the wheels are 0.5 meters, and then we have 3 questions. Find the angular acceleration of the wheels, find the initial linear velocity of the car, and find the final linear velocity of the car. All right, so to start with rotational kinematics is very similar to regular kinematics. All we have to do is change all of the linear variables with angular ones. So instead of position, we'll have angular position. Instead of velocity, we'll have angular velocity. And instead of acceleration, we'll have angular acceleration. All right, so to start, the first question asks to find the angular acceleration of the wheels. So this is a drawing of what the problem looks like. So initially, we're going in reverse, so the wheels are spinning in this direction. And then when we end, we're going forward, so the wheels are spinning in this direction. All right? These are our known variables. So initial is 20 radians per second. Final is 30 radians per second. Radius of the wheel, 0.5 meters, and time taken to change angular velocity is 5 seconds. So to start with, we have to choose a positive direction of rotation. So for this case, I chose clockwise. All right, so we start with our kinematics equations. We have omega final equals omega initial plus alpha t. And then we plug in our variables. So as you see, the final is 30. And something to note is that the initial angular velocity is negative 20 radians per second. And the reason for this is because it's in the opposite direction of the positive direction that we chose initially. So the angular acceleration or angular velocity initially is in the counterclockwise direction, which is opposite of clockwise, so it's going to be negative. Then we also have the plus alpha t, and the t is 5 seconds. Now we have an equation with one variable, so we can solve for angular acceleration. So when you solve it, you get 50 radians per second divided by the 5 seconds, gives you 10 radians per second squared. Are there any questions on this part of the problem? No? All right, then we move on to the second part of the problem, which is to find the linear velocity initially. So this one, we have to relate linear with angular. So the way you do that is you multiply the angular with the radius, and that'll give you the linear velocity. So we take the angular initial, multiply by the radius, and that gives us our linear velocity. Are there any questions on how to do this part? All right. And then part C is the same thing, only for the final velocity. So we have the same equation, but different numbers. And as you notice, V initial is negative, which should make sense because it's going in the negative direction. Then V final is positive because it's going in the positive direction. All right. Any questions on this problem? No? All right. So we'll move to, let's see, the next problem. All right. So this one has to do with energy. rotational energy. All right? So Bob, Tim, and Mike are standing on a merry-go-round that is rotating at an angular velocity of 15 radians per second. Bob has a mass of 100 kilograms and stands at the edge of the merry-go-round. Tim has a mass of 180 kilograms and stands halfway from the center of the merry-go-round to the edge. Mike has a mass of 120 kilograms and stands a distance 2/3 the radius from the center. The radius is 2 meters. Which kid has the most kinetic energy is the question. Also note, we are going to treat each kid as a point mass, so the moment of inertia, when we calculate it, is going to be mr squared. All right? So we'll have our drawing here. We have the 3 kids on the merry-go-round at their respective distances from the center. We have omega, so we're given omega, that's the angular velocity of the merry-go-round. We're given all the masses, and we're given their distances from the center of rotation. So the question asks to find which kid has the most kinetic energy. So to do that, we have to find the kinetic energy of each child, right? So we'll start with mass 1, Bob. So if you remember this equation, very similar to kinetic energy in linear motion. This is rotational kinetic energy, 1/2 moment of inertia times omega squared. All right? So we're going to take 1/2 times the moment of inertia of the first child, and then we're going to multiply by omega squared. Omega is the angular velocity of the merry-go-round. All right? So go step by step. We know I is going to be calculated as mr squared, so we substitute that for I. And we're going to use mass 1 because that's what we're looking at, and then also we're going to use radius 1 because that's what we're working with. All right, so mass 1 was given as 100 kilograms, and then R1 was given as 2 meters because he's all the way at the edge of the merry-go-round. And then the angular speed is given as 15 radians per second. So we plug in all those values and we get 45,000 joules. All right, that's a lot of energy. Also note that for the sake of energy, it doesn't matter if you put in a negative or a positive omega, because when you square it, it's always going to be positive. So there's always going to be a positive kinetic energy. Okay, so then we move on to the second child, and we do the same thing, only now we're going to have different values for m and different values for r. Omega is going to be the same. So we have 1/2 I2 squared, or I2 omega squared. I2 gets substituted with m2 R2 squared. All right. Now m2 is 180 kilograms, and he's standing at half of the radius. So we're going to take half of 2 meters and then square it. And then omega is still the 15 radians per second. We also square that. And then we end up with 20,250 joules. All right. And then finally, we do the third child, very similar to the second one. So we do the 1/2 m3 r3 squared, omega squared. All right. And then m3 is given as 120 kilograms. And this child is standing 2/3 the radius, so that's where the 2/3 comes from. Then times the 2, which is the radius. Square that, then we have omega squared. And then when we calculate that, we get 24,000 joules. So it turns out for this problem, the first child, which is Bob, has the most kinetic energy. So does anyone have any questions on kinetic energy, rotational kinetic energy? Anything about this problem? Everyone's good? All right. So we'll move on to the next problem. I'm actually going to skip this one for now. Let's do. I'm going to skip this. Okay. So we're going to do this problem. This one has to do with torque and Newton's laws. So a mass pulley system is drawn below, which you can't see yet. M1 is 80 kilograms, M2 is 100 kilograms, The mass of the pulley is 50 kilograms. The radius of the pulley is 0.2 meters. The height of M2 above the ground is 5 meters. The moment of a disk is 1/2 mr squared. And the question asks to find the linear acceleration of the system and the time it takes for M2 to hit the floor. And so you'll understand everything when I show you the picture of what's happening. All right, so this is what we have for the problem. Those are all our givens. We're given both masses. We're given the mass of the pulley. We're given the radius of the pulley. We're given the height that M2 is above the ground. And we're given the formula to find moment of inertia for a disk, which is what the pulley is. All right. So, something to note here when we do these types of problems, we're going to be dealing with torque because of rotational. And we're also going to be dealing with Newton's second law linearly. So we're going to be dealing with net force. And with these types of problems, we're going to be combining those two in order to find what it is we're looking for. And in this case, we're looking for linear acceleration. All right, so to start off with, we need to choose a positive direction. So right here, I've chosen clockwise to be the positive direction. Note that it doesn't matter which way you choose. Typically, it's best to choose the way you think it's going to go. That'll get rid of negative signs if you're right. And so I believe it's going to go to the right because mass 2 is going to cause the acceleration. So that's why I chose clockwise as positive. Now, if we look at the pulley itself, we have two forces acting on it. We have tension 1 and tension 2, both acting downward on both sides, right? Because of the two masses. And then over here we have the force diagram, so free body diagrams for both masses. It's over here. And then we just write our Newton's second law for both rotational and for linear. So over here we have net force equals mass times acceleration. So this is going to be the net force or the sum of forces on mass 1. So I've said that clockwise is going to be the positive direction. And if we look at the diagram, if it's going to go this way, right, then anything that moves in this direction is going to be the positive direction. So if we look at mass 1, it's going to move up. So anything up is going to be the positive direction for mass 1. So tension is going to be the force that's acting up, so that's going to be positive. And then we have the weight of mass 1 acting downward, so that's going to be a negative force. So then we get T1 minus the weight of mass 1 is equal to mass 1 times the acceleration, the linear acceleration. All right? Now, if we do the summation of forces for the second mass, we look back at the diagram, anything that moves in this direction is going to be positive. So mass 2 is moving down, so anything pointing down is going to be the positive direction for mass 2. So we have the weight of mass 2 pointed downwards, and we have tension 2 pointed upwards. So the weight is going to be positive, and the tension is going to be negative. So we get m2g minus t2 equals m2 times the linear acceleration. And note that when we do the force statements, and we have ma, the m that we use is going to be the m that's being analyzed in the force diagram. So this one we analyzed mass 1, so we're going to use mass 1 for the acceleration. And same for m2. All right. Any questions on Newton's law for force? All right. Now the newer thing is the net torque. So this is also Newton's second law, but with rotational. So we replace torque, and then don't forget to include this part, this m1g sine theta, in here. All right.
What are we trying to find this problem?
This problem is asking to find mass 2. All right. How to use cosine instead of sine? Okay, so we're going to look at this, right? mg is pointed straight down, correct? So we're going to break these into components. One that's going to be perpendicular to the incline, which is this one. And then we're going to have a component that's parallel to the incline, which is this one. Okay? Now, if we're looking at normal force, the only vector that's counteracting this normal force is this perpendicular component of the mass or the weight. Okay? Now this theta, by geometry, is the same as this theta of the incline. Okay? Now if we just do trig, you can do SOHCAHTOA right here. So we want this component, right? I'll call it x for right now. So we want x, and we have the hypotenuse of the triangle, right? So if we do, this is adjacent to the angle, so we're going to do cosine. So if we do cosine theta is equal to adjacent over hypotenuse, right? So we have adjacent over hypotenuse. The adjacent is x, and the hypotenuse is the m1g. All right? And so if we solve for x, because that's what we care about, you'll get x equals m1g cosine theta. Make sense? And then the opposite for this component is sine theta for the same reason. You just do SOHCAHTOA, and that's how I got this sine theta over here. All right? So then we have this equation right here. Let me just put the final equation, adding the m1g sine theta. So we'll have tension is equal to m1 mu k g cosine theta plus g sine theta plus linear acceleration. All right, so this is the correct equation. Okay, now we do the free body diagram for mass 2. This one's actually simpler because it's just vertical. There's nothing in any other direction, just vertical. So again, we chose up the incline to be the positive direction. So if we follow that direction, anything that goes down for mass 2 is going to be positive. So the weight is down, so that's going to be in the positive direction. So m2g, and then t2 is acting up, which is the negative direction. So we have m2g minus t2 is equal to m2 times a. Okay? Then we solve for t2, and we get this equation. So we have an equation for t1, and we have an equation for t2. Okay? So now, the fun stuff, we deal with torque. So we draw the pulley, and we try to analyze the different torques that are acting on the system. So we have two pulleys, both have different masses, and then they both have different radius, or radii. So we have tension 1 acting this way on the large pulley, and then we have tension 2 acting this way on the small pulley. And then our positive direction is clockwise. So then if we do summation of torques is equal to moment of inertia times alpha. Notice we're going to have two torques because there are two forces acting at a distance from the center of rotation. And also notice that for moment of inertia, we're going to have the sum of moments because there are two pulleys. So how we would have sometimes adding two masses when we do force diagrams, we're going to have an addition of moment of inertias. All right. Now, if we look at this pulley, we have to analyze which is going to give you a negative torque and which one's going to give you a positive torque. So if we look at T1, this force is going to pull the pulley in the counterclockwise direction. So that's going to be a negative torque. All right. And again, these are acting perpendicular to the radius. So when we do sine theta, we'll get 1. All right. So we have a negative T1R for the torque due to tension 1. And then for this one, the tension is going to cause the pulley to rotate in the clockwise direction, which we said is positive. So that's going to be a positive torque. And also notice that it's acting at 1/2 of r because it's on the smaller pulley. So we have these values. Then for the moments of inertias, we have two different ones, 1/2 mr squared. So this is for the big pulley. And then this one is for the smaller pulley. So 1/2 m2 and then half of the radius squared. All right? And then similar to the last one, we don't care about angular acceleration because we don't know it. We'll use this equation to substitute linear acceleration. All right? And now when we do that, a lot of the r's cancel out. And we'll be left with this equation. So we have the two forces over here, and then the different masses, and then the linear acceleration. We have an equation for T1 and for T2 that are in terms of the masses and acceleration. And we have these masses. We're given acceleration. So what we're going to do is plug in our T1 and T2 that we calculated earlier. Just remember that this one has an extra term that I haven't put in. So this is also plus g sine theta. All right. So this is just substituting T1 and T2 into this equation. All right. Now we have an equation that has everything that we know except for m2. So then we solve for m2. We'll get this equation. And then again, just note that there should be a plus g sine theta over here. And this inside this term. Okay. And then the final step is to just plug in all your values. So over here we'll have a plus 9.81 meters per second squared times sine of 30. All right. So when you plug in all those values, you'll get the mass of M2. Just note that this is not the correct value, and I don't have the correct value right now, but I'll post it later today on the website. All right. So are there any questions at all on how to do this problem? Yeah, what's up?
When you did the A over R, how does it cancel out the R squared also?
Okay, so where's that? That is right here. Okay? So if you bring this R to this side, right, and multiply them, you have R squared, and you have R squared, R squared. So all the R's will cancel. All right. The radius, I think, is 0.5 meters. All right. Any other questions on this? They're given. So the large pulley has a mass of 20 kilograms, and the small pulley has a mass of 15 kilograms. Yeah. All right. Any other questions on this problem? All right. So we'll move on to the next one. This one is going to be a simple torque question. So basically definition of torque. Bob just bought the most ratchet shoes ever. These shoes use a bolt instead of a shoestring to tighten. Bob wants to take his shoes off. He has a ratchet of length 0.3 meters. Bob can exert a max force of 132 newtons. And it says a minimum torque of 45 Newton meters is required to loosen the bolt. Will Bob be able to take off his shoes? So this is what we have. This is what's given, the length of the ratchet that he's going to use. This is the minimum torque needed to take his shoes off. And this is the maximum force that he can apply to the ratchet. So there's his shoe with the bolt, and then there's his ratchet. All right. So how can we provide the maximum torque with a given force? F times R, right? So where along this ratchet should I apply the force? At the very end. That'll give us the max torque. All right. Also, what should the angle be between R and F? 90. So if we want to provide the maximum torque, we need to apply all the way at the end of the ratchet, and we need to apply perpendicular to the radius of the ratchet. All right? Does that make sense? All right. So if we do this analysis, we'll just do the basic R times F. So the maximum torque he can supply is the radius times his maximum force. So we have 0.3 meters times his maximum force, 132. And that gives us 39.6 Newton meters. So can he take his shoes off? No. Yeah, sucks, right? No, Bob is too weak, LOL. But then Bob remembered the wise words of his father, work smart, not hard. He then realizes he can accomplish the task by using a longer ratchet. So the next question is to find out how long the ratchet needs to be for him to take off his shoes. So we're going to use the same equation. So the minimum torque needed and the minimum radius times his max force. So does this equation make sense to find the minimum radius of the ratchet? All right. So we just solve for that radius, and we get 0.341 meters. So if he had a ratchet this long, he would be able to take off his shoes. All right. Any questions on torque at all? All right. So we'll move on to the next question. Next question is also torque, but it's going to be a little more complicated. All right. Bob decides to go fishing. He decides to be efficient, so he rigs his fishing rod such that there is an extra fishing string attached to the rod. 2 fish are on the line, so there are tensions in the strings. An alien comes in a UFO and decides to play the claw game to win a prize for his alien girlfriend. The claw grabs the rod as shown below and exerts a force. Force values, angles, and length of the rod are given. The question is going to ask you to find the net torque about the end of the rod, and then also find the direction of the torque vector. All right. So this is the drawing that we have. We got Bob sitting at the end of a pier with his fishing rod of length L. So this is his fishing rod. This is the pivot point. We have one tension here, so this is one of his fishing strings, and this is the other fishing string. And they both have fish, so they're going to have tensions. And then here's the UFO grabbing the rod at this distance, okay? And then we're given a whole bunch of angles and a whole bunch of forces. And we're also given the length of the rod. So we need to find the net torque. There are 3 forces that are at a distance from the end of the rod, so we're going to have 3 different torques. All right, so similar to the other questions, we need to figure out a positive direction, and this one is arbitrary. You can pick which way you want. I just picked clockwise again. We have torque 1, torque 2, and torque 3. All right. Now, if we're going to analyze the first torque, so the torque due to tension 1, that's what I'm looking at right here. So tension 1 is acting straight downward, and then the radius always points from the rotation to the applied force. All right? So if we it would start here and end over here. So if we wanted to find the angle that we care about, we need to move the radius so that it starts here. And that's how we get this little diagram. All right? Now we're given this theta, which is theta 0. That's what this theta is. So theta 0 right here. And then because tension 1 is acting straight downward, we have 90 degrees here. All right? So the theta that we care about when we do sine theta is going to be this large theta right here. So that's going to be the 90 plus theta 0, all right, which is given. And we get 110 degrees for the theta. So now when we do torque, the torque equation, we have RF sine theta. And for torque 1, the radius is L2 because it's being applied across this distance. And then we have tension 1, that's the magnitude of the force, which is given. And then we just found the angle, so we can do sine of that angle. So when we plug all these values in, we get something that's not here yet. So we'll go on to the next torque. So this one we're dealing with the torque due to tension 2 over here. And if we do the same little diagram, we have tension 2 adding, or moving at an angle this way, right? And then we extend the radius again, the same way we did it over here. And we have theta 0 right here. And then over here, we have theta 2, which was given right there. So we have the theta 2 plus that little theta 0. Okay? So for tension, or the torque 2, the theta is going to be the addition of those two torques, or those two angles. So then we get 20 plus 30, that gives you 50. All right? Then you do the same equation, torque equals RF sine theta. And then we plug in our values. So this one's adding, or being exerted all the way at the end of the rod. So it's going to be the whole L, and then times the magnitude of T2, and then times the sine of the angle between. Sure. Is that better? All right. So yeah, this one's theta 0, and this one's theta 2.
I thought you had to take the angle of that side.
So the way that works is if you choose counterclockwise to be the positive direction, you need to start at R and go counterclockwise till you hit it. But the way I'm doing this problem is that, I'll show you at the end, but I'm considering all of the clockwise forces to be positive. So then I don't need to deal with that outside thing. Just deal with the angle between them. All right. So then if we didn't plug in the values yet. But then we do the same thing with the UFO right here. So we have the radius still acting upward. And then we have the UFO tension acting straight up. And then theta 3 is given in the diagram right here. And that's actually going to be the same theta that we're going to use for the torque equation. So same thing, we have R times F times sine theta. Now see, this is what I'm talking about. We have a negative sign here. The theta was given for this one. Oh, okay. Theta 3. All right. So we go back down here. I have a negative 3/4 L T3 sine 70. Now the negative sign comes from just looking at the diagram. So if I look at T3, that force is going to cause the rod to rotate this way, right? The counterclockwise direction. And that's the negative direction. So I can just plug in the negative right there. And that's how I get this negative. And then that allows me to use the angle in between them, regardless of if it's this way or this way. Just use the smaller angle between them. All right, so that simplifies your equations. All right, and then just to get the net torque from the equation above, you just add all the torques together. So this is from torque 1, torque 2, and then torque 3, which was negative. Plug in all those values, and you get a final net torque of negative 617.051 Newton meters. Now what this negative sign means is that the resulting torque is causing the rod to move in the negative direction. So if I add all these torques together, the resulting torque is causing it to rotate counterclockwise. Okay? Now the last question for this problem is to find the direction of the net torque vector. So for this, we're going to need to apply the right-hand rule. Okay? So if we know that the net torque is going to cause it to rotate counterclockwise, we can use the second right-hand rule. So the way that one works is you grab your right hand and you put your fingers and curl them in the direction of the rotation. So if we look at the picture, the net torque is causing it to go this way, right? So we're going to put our fingers curling like this, and then your thumb points in the direction of the torque vector. So if we do that, the torque vector is actually pointed outside of the page. So it's coming out of the page. Does everyone see that? Any questions on how to use that right-hand rule?
Right next to the torque 3, you said that if it goes to the right, which is the opposite of what the right. So that's now it's
Okay, so this is just something we can arbitrarily choose to work out the problem, right? And then when we get to the final answer, we get a negative torque, right? So what that's telling us is the torque is actually working in the negative direction, so the rod is going to spin the other way.
We're not using that because we're now, later, we'll go back to this.
So this positive is used to find the to calculate the torques. And when you find the torque, this negative sign will tell you which way it's actually spinning. So this negative sign means that it's going counterclockwise. If I had chosen the other direction to be positive, this would be a positive number, which would also tell me that it's going counterclockwise. So either way you do it, you'll get the same analysis. And so the torque vector points out of the page. All right? Any questions on this problem?
For torque 3, why did you, for your radius, why was it 3/4?
Okay. So it's 3/4 because we need the length from the end of the rod. So we have L/2 here plus the L/4. All right. Any other questions on this problem?
How did you get the angle to be negative?
All right. So this is just looking at the rod. So if we looked at T1, that force is going to cause the rod to move in the clockwise direction, right? So that's positive. Same for T2. It's going to cause it to go clockwise. Now if we look at T3, it's pulling up on the rod, right? So that's going to cause the rod to rotate counterclockwise. And we already said clockwise is a positive direction, so counterclockwise has to be the negative. So that's why we get the negative value.
So we don't actually know the angle of the final torque, we just know it's pointing out of the page?
It's pointing directly out of the page. So it would be 90 degrees from the plane of this paper. So pointing straight up.
Would it be from the center of rotation to
What do you mean?
straight out?
Yeah, it would be here, pointing straight up. All right. Any other questions on this problem?
How do you know exactly which point is the pivot point?
Which point is the pivot point? So the problem stated that it was, okay, I see what you mean, but I should have made that clear, but it's the end of the rod that's connected to the pier, not the other end. All right? All right. No more questions? All right, so if you didn't want to analyze the direction of the torques, you would use, so we said clockwise is the positive direction, right? So when we do R cross T, we need to go from R and go clockwise until we hit T, and that's the angle we're going to use, okay? So for both T1 and T2, we're going to get the same angle, all right? The same angle that we used before. They're going to be positive. But when we get to T3, we need to go from R and go clockwise until we hit T, right? So this angle is actually 360 minus theta 3, right? Now if you did sine of 360 minus 70, that's sine of what, 290? If you do sine of 290, you'll get the same value, only negative. So either way, you'll get the same exact answer. So this is just throwing the negative sign or the negative sign in there because you know it's going to be negative, and so you can use the smaller angle. But if you want to do it the other way, you would not put this negative sign. You put sine 290, and then you'll get a negative answer here in the end. All right. So we'll move on to the next question. So this one is practicing the right-hand rule. This could be a conceptual question or a multiple choice question. A wheel is rotated by a single force. The wheel rotates such that, let me zoom out a little. The wheel rotates such that the torque vector is pointing into the page based on the drawing below. The force is applied at the top of the wheel, and the question asks, in which direction is the force acting? The right? Okay, so we're going to do this using the right-hand rule. So the radius always points from the center to that point, correct? all right? And we don't know which way the force is acting, but we're given the torque. So if we do the right-hand rule, you put your thumb in the direction of the radius, then you put these three fingers, your middle ring and pinky finger, point in the direction of the torque, and it was stated that the torque is pointing into the page, so we're going to point into the page, and then your index finger points to the force. So does everyone got it? So your index is pointing to the right, so the force is acting to the right. All right. Now, what you need to make sure, because I've seen this many times, is that it's called right-hand rule for a reason. If you use your left hand, it is not going to work. So just make sure you're using your right hand when you do these problems. All right. So thumb in direction of R, middle finger in the direction of the torque, and your index is direction of force. Your force is pointing to the right. All right. So pretty basic question. This is another conceptual question, but this one has to do with angular momentum. So comets orbit the sun following an elliptical path as shown below. At which of these 4 points is it going to be moving at its fastest speed? So what do you guys think? Who thinks point 1? Who thinks point 2? Who thinks point 3? And who thinks point 4? All right, so majority think point 4. All right, so like I said, this has to do with conservation of angular momentum. And so the equation for angular momentum is R cross P, which is linear momentum. So R times M times V, right? So L is constant because it's being conserved. M is constant because the comet's not gaining mass. R and V are changing though. As we move across the path, R is changing, which causes V to change, all right? So if we solve for V, we have L over Rm. These two are constant, so the only thing that's changing is R. So if we have a smaller R, it's going to give us a greater value for V. Make sense? So the correct answer is 0.4, which is the closest it gets to the sun, because it has such a small R value that the velocity is going to be greater. Any questions? All right. So yeah, now we're entering angular momentum. So we have Bob and Bobina are spinning on ice initially with arms wide open, like Creed. Bob has a moment of inertia of 20.7 kilograms per meter squared and is spinning at an angular velocity of 8.1 radians per second. Bobina has a moment of inertia of 22.5 kilogram meter squared and is spinning at a rate of 7.8 radians per second. Bob hugs himself out of loneliness and starts spinning at a rate of 14.1 radians per second. Bobina notices this change in Bob and follows suit. She speeds up to 14.5 radians per second. Which skater has the smaller moment of inertia after pulling their arms back? All right, so this is the situation we have. Initially, he has his arms spread out, and then he's going to close them, and it's going to cause him to spin faster. And then same with Bobina over here. All right, and then the question is to compare the final I value for him and the final I value for her and see which one has the smaller one. So if we analyze the first one, this is going to be like a collision for angular momentum. Even though nothing's really colliding, it's conservation of angular momentum. So if it's being conserved, Li needs to equal Lf. Now initially we have, this is the equation for angular momentum, moment of inertia times angular velocity. So we have II times omega I equals IF times omega F. And we're given 3 of those values, so we can solve for the 4th one. So if we solve for IF, we get II times omega I divided by omega F. We throw in all the values that are given, and we get 11.89 kilograms meters per second, or meters squared. All right? And now we do the exact same thing for the second person, Bobina. We get the same exact equation, but just different numbers. We plug all that in and we get 12.10 kilograms meters squared. And so we find out that Bob actually has the smaller I value than Bobina. So are there any questions on this problem?
What are the units? Kilograms per meter squared?
It's kilograms times meter squared. All right. No questions on? So we have 11.89 and we have 12.1. And so that tells us that the first one is less than this one. All right. Any other questions? All right. Let's move forward. All right. So this is an actual collision with conservation of angular momentum. So a rod of mass 50 kilograms and length L is initially at rest and is free to spin about its center. A ball of mass 1 kilogram moves at a velocity of 20 meters per second, as shown below, and hits the rod halfway between the center and the top of the rod. The ball sticks onto the rod and rotates at an angular velocity of 5 radians per second. Okay? The moment of inertia for the rod is 1/12 ml squared, and the moment of inertia for the ball is mr squared. And the question asks to find the length of the rod. So this problem relies on conservation of momentum, angular momentum specifically. And so we're going to have the same equation from before, Li equals Lf. But the difference between this and the last problem is that initially nothing is rotating, right? The only thing that's moving is this, and it's not rotating, it's just moving at a linear fashion. And so we need to do the definition of linear or angular momentum, which is r cross p, right? So this is our initial. All we have is this thing moving, and to calculate that we need r cross p. Now when we look at the final, we're going to have the rod spinning at a rate of omega with the ball attached to it, right? So we're going to use I omega for this, for the final. Okay? Now we can change r cross p to rp sine theta. And if we look at this diagram, r is the distance from the center of rotation to the ball, and then theta is the angle between r and p, so this theta. And so if we were to do r sine theta, using trig, r sine theta is actually just this height right here. And it's constant no matter where the ball is. So once the ball's here, it's still L over 4. Okay? So if we notice that, we can replace r sine theta with L over 4. So that's what this r sine theta turns into, L over 4. And then we just have regular linear momentum, which can be calculated as m times v. The mass of the ball is given, and the velocity of the ball is given. Now if we look at this side of the equation, we have the addition of moments of inertia. And the reason for that is we have a rod and we have a ball attached finally, right? So we need to add those two moments of inertia. Similar to when we have linear momentum and they stick together, we add the two masses. When we have angular momentum and they stick together, we add the two moments of inertia. So for the rod, it's given that it's 1/12 ml squared. And for the point, which is the ball, we have mr squared. And for this case, r is the distance from the center of rotation to where it's finally at. So we're going to have L over 4 as r. So we throw that in there, and then we square it. Then this whole moment of inertia is multiplied by omega. Now we have an equation with all knowns except for L, which is what we're looking for. So we're going to solve for L, just algebra. So you get this equation for L. All right. And then finally, you plug in all the values that you're given. So all the masses, the linear speed of the ball initially, and the angular speed of the combined masses at the end. So when you plug in all those values, you'll end up with 0.236 meters as the length of the rod.
Can you explain again how you got the different radii?
The different radii? Okay, so this moment of inertia for the rod is the moment of inertia for a rod that's spinning about its center. Okay, so we don't really need to change anything. We just do 1/12 ml squared, where we're given the mass of the rod, and we don't know the length of the rod. That's what we're searching for. Now, for the point mass, it's mr squared, and r represents the distance from the center of rotation to where that mass is. All right? So if you look over here, the mass sticks right here, and this distance from the center of rotation is L/4, because that's where it hit initially. So this is going to be the radius that you plug into this. All right? That's how you get this moment of inertia.
Sine of theta goes to 1, right?
For which case? Right here?
Yeah.
Okay, so it doesn't go to 1. The only way sine theta can go to 1 is if it's at 90 degrees.
I thought it was 90 degrees.
That depends on where you're analyzing. So when it hits, then yeah, sine theta will be 1, and r will be L/4. So you could do it that way too.
Is that what you use?
That's not the way I analyzed it, but that way does work.
Okay.
So I picked an arbitrary point along the path, and you have r right here, right?
Yeah.
And you have p this way, and the angle between them is this, that theta. And so if you just use trig, because this is just a right triangle, right? If you use sine theta is equal to opposite over hypotenuse. So the opposite of this angle is the L/4. And then the hypotenuse is r, right? So if I throw r over here, I get r sine theta equals L/4. And so I substituted this whole thing for L/4 right here. So the r sine theta went away and just turned to L/4. Yeah, you don't need to know theta because it's constantly changing, but the ratio is staying the same. All right? Any other questions on this problem? Okay, so this equation right here, Li equals Lf, is the fundamental for conservation of angular momentum. So this is basically saying that the angular momentum is not changing. All right? And so similar to collisions in linear motion, we always have conservation of momentum unless there's an external force acted upon it, right? So in the case of angular momentum will always be conserved unless a net torque acts on the system, okay? So in this case, there's no net torque acting on the system externally. All internal torques cancel out, so we don't have to worry about like once it hits, because it'll stay conserved. Does that answer your question? All right. You have a question?
So usually in some of the practice problems I did, they don't give you the moment of inertia, so you use usually the right for everything. How is it derived for a bar?
Okay, so
Now you can use volume revolution for like a sphere or something, but how does that work for regular?
all right, so this is kind of out of the scope because Del Barco said he'll give you the moment of inertia. So if you have a weird shape, he'll definitely give you the value like this. But just to answer your question, you'd have to solve the integral of r dm, or yeah, or something like that. All right, so move on to the next one. Actually, I'm going to skip this one and go to the next one. So this is another angular momentum conservation problem. So the question reads, a tortilla is spinning at a rate of 1 radian per second on a frictionless surface. Bob drops his arepa onto the tortilla. The arepa is spinning at a rate of 5 radians per second in the opposite direction of the spin of the tortilla, and they eventually start spinning together. The mass of the tortilla is 10 kilograms, the mass of the arepa is 20 kilograms, and the radius of the tortilla is 2 meters, and the radius of the arepa is 1.5 meters. So these are really big tortillas. The moment of inertia for both disks is 1/2 mr squared. And the question asks to find the angular velocity of the tortilla arepa combo. So this is the drawing of what's happening. We have a tortilla spinning in this direction with a certain angular speed, and we have the arepa spinning in the other direction at a certain angular speed. What's going to happen is it's going to drop onto it at the center, and then eventually they're both going to start spinning together. All right? So this is another like form of a collision dealing with angular momentum. So here are all the values that were given. And now what we need to do is like the other problems, we need to define a positive direction. So I'm going to state that anything moving in this direction is positive. Okay? So we do Li equals Lf. So initially we actually have two different angular momentums, one due to the tortilla spinning and one for the arepa. So this one is going to be for the tortilla because it's in the positive direction of motion that I defined. See how omega is the same direction? So it's going to be positive. But if we look at the arepa, it's going in the other direction, right? So we need to make that negative to show that they're in opposite directions, all right? So we have I1 omega 1 minus I2 omega 2. And now if we look at the final scenario, we have both of them connected to each other, and they're both spinning at a constant, or at the same angular speed, okay? So I don't know which way this is actually going to go, but I'm just going to assume it's going this way, and then we'll see what happens. So we have to add the moments of inertia again. So we have I1 plus I2, and they're both going to be spinning at the same rate. So we can multiply them both like that. All right? And we're given everything except for omega f, so we can solve for omega f, and then from here we can throw in all our values. So we need to replace all the i's with 1/2 mr squared, and we have to note that the 1/2 mr squared has to do with that specific object. So I1 has to do with the tortilla, so we need to use the mass of the tortilla and the radius of the tortilla. And then same with that arepa over here. All right? To simplify, we see that all the 1/2s cancel out. And then we're left with this equation. And then from here, we just plug in all the values that were given. Note that I don't put a -5 radians per second here, because I already included the negative out here. Okay? So then when we solve this, we get a -2.176 radians per second for the angular velocity. So what that tells me is, since it's negative, that the final rotation is actually going to be in the other direction. So when the arepa lands and they both start spinning at the same rate, it's actually spinning in this direction. Make sense? All right. Are there any questions on this problem? No?
Can you repeat what you said before about the radius? Like it was negative before, but then you accommodated that for...
Okay. So when I did this analysis, I said this is positive direction. If we look initially, the arepa is spinning in the other direction, so that's going to be a negative angular momentum. So I just threw the negative sign right here. And so when I go to plug in for omega, this omega 2, I don't want to put another negative in here because I already did that in the initial assumption. So if I put a negative here, it would become a plus, and then now your equation thinks that the arepa is spinning in the same direction, and you're going to get a different answer. All right, so be careful with signs. All right. Any other questions on this problem? No? All right. Okay, so now we're moving on to oscillations. So this is a simple oscillation problem. All right, so we have a pendulum. The mass at the end of the string is 5,000 kilograms. The pendulum is on the surface of the Earth. The period of this pendulum is 2 seconds, and the question asks for 3 things. We want to find the frequency, the angular frequency, and the length of the pendulum. All right, so this is what we have here. Just have a random pendulum, mass, and a length. We're given the period, and we're given the mass that's attached to the string. All right. And so, to find the period, or to find the frequency, we have this equation for period. Period is the inverse of frequency. All right. So we can actually just solve that right away. So frequency is 1 over the period. So we have 1 over the 2 seconds. That's going to be equal to 0.5 hertz. So hertz is the SI unit for frequency, and it's equal to 1 over seconds. All right? And what frequency represents is how many cycles this pendulum is going to do per second. So 0.5 hertz means that it's going to do half a cycle in 1 second. So in 1 second, it's only going to make it to this other side. And then it's going to take 2 seconds to reach its original position. All right? Now to find omega, we have to relate omega with frequency. And so to do that, we have this equation, omega equals 2 pi f. So we just found f, then we have 2 pi. We multiply that, we just get pi radians per second. So radians per second is the units for omega. And if you think about this equation, it really is just conversion. So if you do dimensional analysis, frequency is cycles per second. So frequency is cycles per second, right? And we want to get to radians per second, right? So we need to figure out how many cycle or how many radians are in a cycle. So there's 2 pi radians in a cycle, right? So we have 2 pi radians per cycle. And then when we do this, the cycles cancel out, and you're given radians per second as the units. So 2 pi is your conversion factor. So it's very similar to just converting centimeters to meters or any other unit. So just in case it doesn't make sense to you. But these formulas are on the formula sheet, if I'm not mistaken, so don't need to worry too much. And now the question asks to find the length of the pendulum. So we got to use this equation, which is also in your formula sheet. So omega is equal to the square root of g over L, where g is the gravitational acceleration. And because it's on Earth, we can use the 9.81. If it were on a different planet, you'd have to use the different g value for that planet. So we plug in, or we solve for L, we get g over omega squared. And then we just plug in all our values. So we have 9.81 meters per second squared for g. And then we have pi radians per second, which we just calculated over here. We're going to square it. We're going to divide the two. And we get that the length of the pendulum is 0.994 meters. All right? Now, what do we notice about the mass? It's very large. But did it affect anything in our problem? No. So, like Del Barco said in lecture, the mass of a pendulum doesn't affect anything about its properties. So it doesn't affect the frequency, it doesn't affect the period, and doesn't affect the angular frequency. Okay? Now this is going to be different for a spring system, where the mass does affect the oscillation of a spring system, which is actually going to be the next problem. So does anyone have any questions on this? Any of these calculations? No? All right. So we're going to move on to this hefty problem. So a mass is attached to a spring on a horizontal frictionless surface. The mass is pulled a distance and released. At a time of 2 seconds after being released, the mass is located 3 meters from the equilibrium position. The angular frequency of oscillation is pi over 6 radians per second. The mass of it is 100 kilograms. And then the question asks for several things. Find the amplitude of oscillation, the spring constant, the maximum potential energy of the mass, maximum kinetic energy of the mass. Also, if at a random time the kinetic energy is 293.48 joules, what is the potential energy at that same instant? All right? So this is going to be a good problem to go through for oscillations. So this is what we're looking at. So this is the mass at equilibrium with the spring. And what's happening is we're stretching it to an unknown distance, and then we're going to let go of the mass. When we let go, after 2 seconds of letting go, the mass is going to be at this distance, which is given to you as 3 meters. All right? So we're also given the angular frequency of the oscillation, and we're given the mass. So what we need to start off with is equations of motion for an oscillation. So this formula is given in your formula sheet. It's actually the only one equation of motion given to you. But to find velocity and acceleration from this, all you have to do is take the derivative, right, with respect to time. So x, the way this equation works is that if I plug in a certain time value, I'll know its position at that time with respect to the equilibrium. All right? But this problem is kind of like working backwards because it gives us a time and it gives us the distance at that time. And we can use that to find the amplitude of oscillation. So we have x sub t is equal to a cosine omega t. So if we solve for a, we get x of t divided by cosine omega t. And the specific time we're given is 2 seconds. So we just plug in 2 seconds for both of the times. And we're given that the position at 2 seconds is 3 meters. So we can plug in 3 meters for x of t. And then for cosine, we have omega t. Omega was given as pi over 6 radians per second. And then we have the time as 2 seconds. Okay? So then when we do this calculation, we have 3 meters over 0.5, because this turns out to be cosine of 60 degrees. So 3 meters over 0.5 gives us 6 meters. So this 6 represents our amplitude of oscillation. So this is the max distance from the equilibrium that the mass can reach in both directions. So it'll stretch 6 meters, and then it'll also compress 6 meters. And it'll just keep going back and forth. All right. Are there any questions with this part of the problem? No? All right. So then the second part is to find the spring constant. And the way we can do that is omega equals the square root of k over m, which is another formula given to you. We're given mass, we're given omega, so we can solve for k. So k is equal to omega squared times m. We have pi over 6 squared times the mass, 100 kilograms. Then when we calculate that, we get 27.416 newtons per meter. All right. So that's the spring constant. The next question asks to find the maximum potential energy of the mass. So at which point is the potential energy max along this oscillation? Huh? The endpoints? All right, so when it's fully stretched and when it's fully compressed is when we're going to have the maximum potential energy, right? And this maximum potential energy is in the form of what? The spring force, right? So the spring is going to store energy. And so when it's over here, it's stretched and it's going to have an energy associated with it. So the equation we're going to use for the max potential energy is going to be the regular spring energy equation, which is 1/2 kx squared. But to get the maximum potential energy, we need to use the maximum x value. And the maximum x value is the same as the amplitude, right? So we have 1/2 k amplitude squared. And we have all those values because we just calculated them. And then finally, we get 493.48 joules. All right? Does that make sense to everyone? All right. Now the next question is to find the maximum kinetic energy associated with the mass. So at what point on this oscillation is there going to be the maximum kinetic energy? In the middle, right? as it passes through the equilibrium, there's going to be no compression or stretch in the spring, so there's no potential energy in the spring. All of it is going to be kinetic energy associated with the motion of the mass. So the same thing is we're going to use the equation for kinetic energy, which is 1/2 mv squared, right? But we need to use Vmax. And we need to figure out what Vmax is. So we go to the equations of motion. So this is the equation of motion for velocity for an oscillation, which is just the derivative of this position. So if I took the derivative with respect to time, I'll end up with a negative a omega sine omega t. All right? Now, to maximize V, we need to maximize all of its components. A is a constant and omega are constant, right? But sine is changing over time. The maximum value that sine can be is 1, right? So if we want V max, we need to replace sine omega t with 1 because that's the maximum value it can be. So then your V max becomes a omega. All right? Are there any questions on that? I was looking at the formula sheet, and this is the only one that's given, the position one. So if you needed to find the velocity or the acceleration, you would have to take the derivative of this. All right. So does everyone see how a omega is the value for the maximum velocity? All right, good. So
How did you get the 1/2 Ka squared?
1/2 Ka squared. So this comes from spring energy. So the potential energy of a spring is 1/2 Kx squared, right? And this x represents the distance from equilibrium. So if the spring is stretched or compressed a certain distance, it's going to have an energy associated with it, right? Now, if we want the maximum potential energy, we need to maximize this. K is a constant, right? So it's not going to change. 1/2 is just a number. X is the only thing that's changing as you're oscillating. And so we need the maximum X value to get the maximum potential energy. And it turns out the maximum X value for a spring system is going to be the amplitude, because that's the farthest it gets stretched or compressed.
Since this is a closed system, can't you just say that there's no energy lost between maximum potential and maximum kinetic and just say they're equal to each other?
Okay, so we're going to get to that. And when we do the maximum kinetic energy, we notice that we get the same exact value, right? And for the reason you said, it's a closed system. There's conservation of energy. So all that's happening in this system is the energy is being transferred from potential to kinetic. So over here, we have maximum potential, and we have no kinetic because it's at rest, right? And when it's passing through the equilibrium, we have maximum kinetic, but no potential because it's not being stretched or compressed. So that's why, in the end, when you do this calculation, you'll get the same exact value here. All right? So this is a way to check to see if everything's all good. Now, if there was friction, this would be a whole different story, right? So energy would be lost as you're oscillating. So they wouldn't be the same. All right? So then the final question is, at a certain point in time, we're given that the kinetic energy is 293.48 joules. All right? So then we go back to this equation, E equals K plus U, and we're given a K at a certain time, right? So that's the 293.48 joules, and we know it makes sense. Concerned about the sign of the velocity, but also note that even if I did use the negative, right? When I do K max, I get 1/2 mv max squared. And so even if I put a negative velocity here, it would square and become positive, because kinetic energy is always positive. So don't worry too much about that. Are there any other questions? All right, and here are some conceptual questions about oscillations. So at which points are the acceleration going to be maximized? So when do we have the most acceleration? Where? At the endpoints, okay? So at the very end here, when it's fully stretched or when it's fully compressed, we're going to have the most acceleration, because if you remember Hooke's law, we have F equals kx, technically negative kx, is equal to ma, Newton's second law, right? So we're going to have the most acceleration when x is the most. So when it's stretched, we're going to have a larger acceleration than when it's not stretched. So when it's actually in the middle, right, we're going to have 0 acceleration because the spring isn't being stretched or compressed. All right. Let's see. So the last part of this problem was just to analyze that in between the equilibrium and the maximum stretched or compressed, we have a combination of potential and kinetic energy. All right, so that's just what the last question was asking. Also, if you wanted to find the acceleration at a given time, how would you do it? Right, so you would take the derivative of this. When you do that, acceleration becomes negative a omega squared cosine omega t. And again, just want to tell you that these negative signs just inform you of the direction of oscillation. All right. So then if it's at a specific time, you're just plugging the time because you already know the amplitude and you know omega. All right. So that's how you do that. Okay. So that's it. All right. So are there any other questions on that? Okay. So we still have time. So I'm going to go back to some of the ones that I skipped. So, all right. We'll go back to this. So this is rotational kinematics. We have a large wheel of cheese initially at rest, and it accelerates at a rate of 10 radians per second squared. The radius of the cheese is 2 meters. Find the time it takes to complete 10 revolutions. Find the angular velocity at the moment the cheese wheel hits 10 revolutions. And then find the distance the cheese wheel has traveled across the ground in 10 revolutions. All right? So this is what we have, just a cheese wheel rotating, initially at rest. So, like I said in the beginning, rotational kinematics just uses the regular kinematics equations, but replacing everything with angular quantities. So, if we use the angular displacement is equal to initial angular velocity times time plus 1/2 angular acceleration times time squared, we can find the time it takes to hit 10 revolutions. But first we need to find the delta theta. So this is the angular displacement for 10 revolutions. So 1 revolution is going to be 2 pi's angular displacement, right? So if we want 10 revolutions, we need to multiply 1 revolution by 10. So then we get 20 pi radians as your angular displacement for 10 revolutions. So then we just use this equation and we have all the knowns. We know this and this, so we can solve for time. When we solve for time, we get 3.545 seconds, right? So that's the time it takes to complete 10 revolutions. Well, the second question asks to find the angular velocity at the moment it reaches 10 revolutions. So again, we're going to use another kinematics equation, which is omega f equals omega I plus alpha t. All right, we're given alpha. We just found t. It's initially at rest, so there's no initial angular velocity. And we're looking for final angular velocity. So then we simply have acceleration times the time. So 10 radians per second squared times the time it takes to do 10 revolutions gives us 35.45 radians per second as the omega. All right. And then the last question is to find the total distance that the wheel has traveled. So this has to do with relating linear motion with angular motion. So if you remember this equation, we have delta x is equal to the radius of the wheel times the displacement, the angular displacement. So we know the angular displacement already was 20 pi radians, and we're given the radius. So doing this, we can find the total distance that the wheel traveled. All right? And to make sense of this, what you can do is find the circumference of the circle, right? So the circumference of a circle is 2 pi r, right? And it's rotating 10 times, so you can do 2 pi r times 10. That gives you the same exact answer. You have a question? All right, so delta theta represents the angular displacement, right? So it's going to be the angle, that's how many times the angle is going around, right? So this is theta. And we care about theta for 10 revolutions, right? So what's going to happen is the wheel is going to rotate 10 times completely. You got it? All right. Are there any questions on this or rotational kinematics at all? No? All right. Let's move on to another one. So, all right, so this one has to do with rotational energy. All right. A fan with 6 blades, each of length 1.5 meters and mass of 5 kilograms, has 500 joules of rotational kinetic energy. Calculate the angular velocity of the fan. Each fan blade is treated as a rod, so the moment of inertia for a blade in this problem is I equals 1/3 mr squared. All right? So this is a picture of our fan, and it's rotating at an unknown omega, and it's given that the kinetic energy is 500 joules. And we're given the mass and the length of each blade. So this is actually a fairly simple problem. We just use the equation for kinetic energy due to rotation. That is 1/2 I omega squared. All right. So the tricky part about this question is to get the I value. So we have 6 different blades. So we're going to have 6 different moments of inertia. But because they have the same properties, they're going to be all the same value, but 6 of them. So basically you do I, which is 1/3 ml squared, right? And you multiply by 6 because there's 6 of them. So then from here you just plug in all the values. So we have 5 kilograms, 1.5 meters for the length. We're going to square that. Then omega is what we're looking for. We're given the energy. So we can find omega by using this equation, and then we end up with 6.667 radians per second. All right? And do we know which direction it's spinning? All right, so the answer is there is no answer because we don't know which way it's spinning. This is kinetic energy, so whatever we get for omega is always going to be positive. So we don't know which way it's spinning, but it's still going to have the same kinetic energy. So it doesn't really matter which way it spins when it comes to energy, because energy is a scalar quantity. All right, so any questions on this? All right. Let me find another one. All right, so all right. So here we have another conservation of angular momentum. All right, so the problem is there's a can of Vienna sausages rotating at a rate of 10 radians per second on a frictionless surface. To two identical cans of Vienna sausages with no spin are dropped on top of the spinning can. They eventually all spin together, and the question asks to find the angular velocity of the cans when they're all spinning together. All right? So this is our scenario. We have one that's spinning, and then these two aren't spinning. They're going to be dropped onto it, and then they're going to start spinning at the same rate. The question is to find this value. All right? So again, we're going to use conservation of angular momentum. So the initial angular momentum has to equal the final. Now initially, all we have is this spinning. So we're going to call that I initial times omega initial. And then for final, we have I final, omega final. Now because they're identical, there's a relationship between the I final and the I initial. So I final is just going to be 3 times I initial, because initially we only have 1 can. In the end, we have 3 cans that are all the same, right? So we just multiply by 3. All right, so then we can plug that in, right? And we notice something. The i's cancel out, right? So we have omega I equals 3 omega f. And then we can solve for omega f, and we're given omega I. So then we get omega f equals 3.33 radians per second. All right? And in which direction is it spinning? Right, so it's spinning in the same direction as this. It would not make sense for it to spin the other way, right? Because these have exactly no spin, so there's no way it could cause it to rotate the other way. All right, any questions on this? Okay. So these are all of my problems. You can get them, you can find them on the UCF Study Union website. I do want to go over a few things that I think will help you for the test. So some study tips, or test tips actually. Test/study tip. Okay. So the first thing I want to mention is units, because I've seen multiple times that units get in the way of getting the right answer. So make sure you convert all units to SI units. All right, so that's the first thing. As for studying, I think one of the best things to do is to look at the formula sheet and make sure you understand how each formula works. All right, so look at the formula, look at all the variables that are there, and understand what each variable means. Okay, so understand all the formulas on the formula sheet and when you can use them. All right. Another tip that I found useful when I study physics is when you get stuck on a problem, which happens a lot, is to look at your formula sheet, because sometimes you don't think you know the answer, but once you look at the formula sheet and you see all those formulas, you start thinking of what you can use them for. And so just look at the formulas while you're doing the test. What else? Does anyone else have any test taking strategies that they use that might be helpful for everyone else? Crying? I don't think that's a good test taking tip. I don't think he'll give a problem like that.
You did mention something about adding friction to oscillations.
Okay.
That would decrease the amplitude or something. So
Right. So you're actually given those formulas. So what she's saying is an oscillation that has damping in it. So if you remember from lecture, we can have something like this, where a mass and a spring is placed into like a bucket of a liquid, right? And if you were to make it oscillate, it would slowly start to stop because of the fluid in there, causing friction. And so he actually gives you the formulas for this. So he gives you the formula for position with respect to time. And then he also gives you the formula for omega d, which is the frequency that's involved here. So when there's no friction, omega is equal to square root of k over m, right? But when there is friction, this is equal to something else, all right? And it's in your formula sheet, and I don't want to write it down because I might get it wrong, but it does depend on k, it depends on m, and it depends on b. And does everyone remember what b is? Right, so b is the coefficient of the frictional force involved with the fluid. So he could give you any of these values and ask, or like he'll give you like 3 of these 4 values and he can ask you to find one of them, right? Using that equation. As far as this type of problem goes, I don't know if he'll ask as extensively as this problem asked because friction is a lot more complicated. So I wouldn't worry too much about that, but he does give you this and he gives you this.
Can I say something else? Something kind of weird. He said something about 2 rotating objects in a collision. And
Okay.
I think he's going to give us something as complicated as that.
So when he says that, 2 rotating things as a collision, we actually did quite a few problems like that. So this one would be one of those.
Oh, so it says like an elastic collision. That's what he meant.
Yeah.
Oh, okay.
So something like this, or the tortilla one, or the rod being hit by the ball. So he'll probably ask one of those questions. You have a question?
Do you think any problems on static equilibrium would show up, like with both the shear modulus and everything?
So for as far as modulus goes, that will probably be, if it's included in the test, it'll probably be a multiple choice. So I wouldn't worry too much about it, but for modulus, you're given all the equations on the formula sheet. So I wouldn't worry too much. You have all the equations. As far as static equilibrium goes, it's possible he could ask that on the test, but what I'm going to tell you here is that for static equilibrium, so like let's say you had a beam, you had a mass, you have different masses, right? So the way static equilibrium is, it's almost exactly the same as the analysis for, let me give you the problem that we did. So for something like this, right? This has acceleration when we solve this problem. If we were going to try to keep this in static equilibrium, so we wanted this system to be stationary, nothing moving, all you have to do is turn all these accelerations to 0. So that's what static equilibrium is. So let me write that down. For static equilibrium, what you do is the net force on the system has to equal 0, and then the net torque on the system has to equal 0. So that's all you need to know for static equilibrium. So you can have something like this, or you could have the pulley system on an incline. All right. Are there any other general questions about the test? All right. So I'm going to pass out a survey for the last 10 minutes. If you could fill it out, and I'll collect them at the end. So I'll just give you a few and just pass it down. Yeah.
What do you stand for?
I'm not too sure. I think it just stands for drag.
Okay.
No, there's no sign issue.
Yeah, I have a question.
What's your question?